This video is all about geometric sequences. The three sequences on the slide there are all geometric sequences. The first one, we can see that we are multiplying by 2 each time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. The common ratio between each set of terms is 2. The next sequence here, our common ratio is 1/3. We are multiplying by 1/3. 81 times 1/3 is 27. 27 times 1/3 is 9. 9 times 1/3 is 3, and so on. The common ratio is 1/3. Here the common ratio is -4. 1 times -4 is -4. -4 times -4 is positive 16. 16 times -4 is -64. -64 times -4 is positive 256. The common ratio is -4. So a geometric sequence is a sequence of numbers where between each two terms you have the same common ratio. You're multiplying by the same number each time. So how do we work out the nth term of a geometric sequence? So if I say that the first term, u1, of my geometric sequence is a. To get to the second term, I'm going to multiply that by the common ratio, whatever it is. Let's just say it's r. So the second term will be ar, because I've just multiplied by r. To get to the third term, I would multiply by r again, so I'd get ar squared. To get to the fourth term, I'd multiply by r again, so I'd get ar cubed, and so on. So what's the pattern here? What's the nth term? Well, just to make it a little bit clearer, I'm going to say that this is r to the power 1. And the first term, a, I'm just going to write that as a times r to the power 0. Obviously, r to the power 0 is 1, so a times 1 is just a. So I'm not actually cheating or changing anything there. It's just hopefully going to make the pattern a bit clearer for you. Because my nth term, well, we can see they all have an a in them. They all have an r, and the power, well, when it was the first term, the power was 0. When it was the second term, the power was 1. Third term, power was 2. Fourth term, power was 3. So when it's the nth term, the power is going to be n minus 1. So the nth term of a geometric sequence is a times r to the power n minus 1. So that's a formula you need to know. So copy that down. What about the sum of a geometric series? What about if I wanted to add up all of these terms? So the first term is a, the second term is ar, the third term is ar squared, and so on. We know the nth term would be ar to the power n minus 1. The term before that would have one less r in it, so ar to the n minus 2. And what sum would I get when I add all of these things together? Now, we saw in the previous video for arithmetic sequences that Carl Friedrich Gauss gave us a little trick for this. And there is a trick for this sequence as well. It's not the same trick, but it's a similar sort of trick. If I say that I want to work out the sum of all of this, so S equals all of these things, I'm going to copy it down again, just like we did in the previous example, in the previous video, but I'm not going to reverse it this time. I'm just going to copy it down exactly to begin with. And then, this is the trick. We are going to multiply that second line by r. So I'm going to times the whole sum by r. So it's going to give me a sum that's r times bigger. The first term will be a times r. The second term, AR times R, will be AR squared. The third term would be AR cubed, and so on. This term here, timesing that by R, will now be AR to the n minus 1. And the last term here, or the nth term here, AR to the n minus 1 times R, will just be AR to the n. Well, why did I do that? Why is that useful? Well, what I'm going to do here is I'm going to subtract the top, I'm going to do the top line, take away the bottom line. I'm going to do everything here, subtract everything here, and you're going to see why. The AR subtract the AR here would cancel out. The AR squared subtract the AR squared would cancel out. The AR cubed subtract the AR cubed would cancel out. This term would cancel out with the AR to the n minus 2 here. The AR to the n minus 1 subtract AR to the n minus 1 would cancel out. So everything cancels out, including all of these dots in the middle. The only thing that would be left is the A minus the AR to the power n. So on the right hand side here, I'm just left with A minus AR to the power n. The left hand side here, well, I did S take away RS. I did the sum take away the sum multiplied by R. That's what I just did here. That was the trick to make all of those things cancel out. All I'm going to do now to get S, the subject, because remember that's what I'm trying to find here, what is S, the sum, I'm going to factorise on both sides. And I'm going to divide. And so that is the sum of n terms of a geometric sequence. Again, you need to know that formula. You need to know how to derive it as well. So you need to be able to do that exact same process that I've just done yourselves. But make sure you've got all that copied down. Now, the next thing we need to talk about is the sum to infinity. I need to talk a little bit about what that means. So what I'm saying here is that I want to work out the sum of an infinite number of terms. So we keep on adding and adding and adding and adding and adding, and we never stop. So I'm not saying the sum of 10 numbers or the sum of 20 numbers or the sum of 100 numbers or 1,000 numbers. What would the sum of an infinite number of these sequences be? Of an infinite number of the terms of this sequence be? Now, this first sequence there, 1, 2, 4, 8, 16, I can't work out the sum to infinity of that sequence. It doesn't make any sense because each time I'm multiplying by 2, the numbers are getting progressively bigger and bigger and bigger. There's no limit to the sum. Soon I'm going to be adding 1 million, then 2 billion, then 4 billion, and so on and so on and so on. I'm adding huge numbers. So the sum to infinity of this sequence, well, because the numbers get so big, we just call that sum divergent. It just keeps getting bigger and bigger and bigger. It makes no sense to try to calculate the sum to infinity of that. There's no point even trying to do it. But that's not always the case with the sum to infinity. For example, this other sequence here, 1,000, 100, 10, 1, 0.1, and so on. In this case, because the common ratio is 1/10, the numbers are getting progressively smaller and smaller and smaller. I can calculate the sum to infinity of this sequence because even though I'm adding an infinite number of numbers, those numbers that I'm adding get progressively smaller and smaller and smaller and smaller. So whilst I cannot literally sit here and keep on adding numbers for infinity's sake, because I know that those numbers are getting so small that they're barely going to actually change the actual size of the numbers I've added previously, therefore I can actually say that the sum to infinity is going to converge to a number. And what's that number? What is it eventually going to become? That's what we mean by the sum to infinity. In this sequence here, by the time I've added, I don't know, let's say 50 terms, if I sat here and added 50 numbers of this sequence, by the time I tried to add the 51st term, it will barely make any difference to the answer whatsoever because that number would be so small. So what is that number that this sum would converge to? So a sequence is going to diverge if the common ratio is bigger than 1 or less than -1. If the common ratio is bigger than 1, then the numbers are going to get bigger and bigger and bigger, and there's no point trying to calculate the sum to infinity. Or if the common ratio is less than -1, if it was -2 or -3, then again, the numbers are going to get bigger and bigger and bigger. They'll change their sign, but they'll still get bigger and bigger and bigger. There's no point trying to calculate the sum to infinity of that sum. Whereas, if the common ratio is between 1 and -1, or I could just say that the modulus of the common ratio is less than 1, if that is the case, then actually from term to term to term, the numbers get smaller and smaller and smaller, and therefore I can calculate the sum to infinity if the common ratio is less than 1. So what's the formula for this? Well, we've just seen a moment ago that the sum of n terms of a geometric series is given by that formula. So if r is less than 1, as n tends to infinity, as I add an infinite number of terms, what happens to this here, the r to the power n? Well, let's think. I am taking a number that is less than 1 and I'm multiplying it n times. Now we know that when I multiply a number by something less than 1, the answer gets smaller. If I multiply by something by half, it gets smaller. If I multiply something by a quarter, it gets smaller. So if r is less than 1, and I multiply that over and over and over and over again, an infinite number of times, then that number is going to tend towards 0. A half times a half times a half times a half times a half. If I keep doing that infinite times, it's going to tend towards 0. And you can say the same for any number that is less than 1. 0.9 times 0.9 times 0.9 times 0.9. If I did that infinite number of times, it would tend towards 0. So as n tends towards infinity, r to the power n will tend towards 0, and therefore the sum of infinite terms would tend to, well, on the numerator I'd just be left with a times 1, and on the denominator I've got 1 minus r. So that sequence I had a moment ago, the 1000, 100, 10, 1, and so on. My first term is 1000, my common ratio is 1/10. So what would be the sum to infinity of this sequence? It would be 1000 divided by 1 minus 1/10, which would be, on your calculator, 1111.1 reoccurring. If I were to keep adding these numbers for infinite terms, that's the number I would get, which hopefully makes sense because what I've just done here is I've added 1000 plus 100 plus 10 plus 1 plus 0.1 plus 0.01 plus 0.001 and so on. That's what this geometric series is doing, and so hopefully it makes sense why we can calculate the sum to infinity of this series and why this is the answer and why this formula works. If I added all these numbers together, of course I'm going to get 1,111.11111111 and so on. Right, let's have a look at an example of a exam type question with geometric sequence. So the first three terms of a geometric sequence are k plus 4, k, and 2k minus 15, where k is a positive constant. I need to show that k squared minus 7k minus 60 is equal to 0. So because it's a geometric sequence, I know that I'm multiplying by the same each time. They have a common ratio. So I know k plus 4 times r is equal to k. And I also know that k times r is equal to 2k minus 15. One way of me writing this down, because they have the common ratio, I could say that k over k plus 4, so this divided by this would give me my common ratio, and also 2k minus 15 over k. This divided by this would give me the common ratio as well. And that common ratio has to be the same. This is like in the previous question, me saying 1,000 divided by 100 is the same as 100 divided by 10. The ratio between the terms has to be the same. So what I can do now is cross multiply. So multiply by k over here, multiplied by k plus 4 over here. And I'll get k squared equals 2k minus 15 times k plus 4. Expand those brackets. And collect up like terms and make it equal to 0. And you can see that is what we needed to show. So that's part A of this question. Part B. Hence show that k is equal to 12. Well, we've got this quadratic equation, so let's solve it. Let's find out what are the possible values that k could be. So k minus 12, k plus 5. That is that equation factorised. So k is either equal to 12 or k is equal to minus 5. But I was told that k is a positive constant. So actually I can ignore the k equals minus 5, and I know that k has to be 12. That's part B of the question done. Now I know that k is 12, let me go back to this original sequence and actually fill in what are the terms. So the first term is k plus 4, so that means that the first term is actually 12 plus 4, which is 16. The second term was k, so that's just going to be 12. The third term, 2k minus 15, so that's 2 times 12, which is 24, minus 5, which is 9, minus 15, which is 9. So these were actually the first three terms of my geometric series. Find the common ratio of the sequence. So what actually was I multiplying by each time here? Well, if I just do 12 divided by 16, which is 3/4. The common ratio here is 3/4. I did 12 divided by 16, I did this divided by this. Could have done 9 divided by 12, as we discussed before. It doesn't matter. The ratio is always going to be the same, no matter which terms you pick. Right, so that's part C done. Part D, find the 10th term of the sequence. So n is 10. So I know A was 16, R is 3/4, and n is 10. So I can use the nth term formula, which remember looks like this. So the 10th term, U10, would be equal to 16 times r, which is 3/4, to the power of 10 minus 1, or 9. If I type that into my calculator, I find that the 10th term to 1 decimal place is 1.2. That would be the 10th number in this sequence. If I kept multiplying by 3/4, once I got to the 10th number to 1 decimal place, it would be 1.2. Excuse me. Part E, find the sum of those 10 numbers. Let's use the sum formula for that. So the sum of 10 terms is going to be equal. Let's just remind ourselves what the formula is for now. So A is 16. Then we then got 1 minus 3/4 to the power of 10 over 1 minus 3/4, which to 1 decimal place is 60.4. So that would be the sum of the first 10 numbers of that sequence. And then finally part F, find the sum to infinity. If I keep adding these numbers for infinite number of terms, what would it converge to? What would it add up to? So let's use the sum to infinity formula, which is A over 1 minus R. A in this case is 16. R is 3/4. So 16 divided by 1/4 is 64. So if I were to keep adding these terms up for an infinite number of terms, the answer would converge to 64. So that's it. That's what a geometric sequence is and how we can work out the nth term and the sum to infinity, and when you can actually do that.